Excuse me.
Okay, well, good morning, everyone, and welcome back. We are now in the course on environmental bioethics, and lots of interesting topics to cover in this course. As I emailed you, it's going to be 7 modules, okay? And we'll go through it in a moment. But as always, I first want to start with a little prayer. In the name of the Father, the Son, and the Holy Spirit.
Amen.
Blessed Trinity, we love you, we adore you, we thank you for all your many blessings in the midst of the trials and difficulties of life, especially right now as we are experiencing this pandemic, Lord, such a dramatic situation with so many people either getting sick or actually dying. We implore your mercy, Lord, your love, your forgiveness, so that we may move forward from this experience, learning that we really need to live a humble life and to be good stewards of the environment, because we know, Lord, from experience that nature never forgives. Nature can't forgive. And we are experiencing one of those consequences right now. We ask for your blessings during this course, during this lecture, particularly as we look at environmental bioethics, our responsibility toward the rest of creation, considering that we are the only species that has truly the capacity to either destroy the world or make it always a better place to live for ourselves and for future generations. As always, we ask for those who are most in most need of your divine mercy at this time. We ask all this in the name of Christ, our Lord.
Amen.
Amen. Okay, any comments first off as we begin the new course for the next 7 weeks? Anything anybody want to share? I hope you're staying safe and that this lockdown may come to an end soon with prudence and faced in an orderly fashion, so we can get back to some sense of normalcy, in particular with regards to our parishes and access to the sacraments, which our people have been without the sacraments for 2 to 3 months now. But just a little notice that yesterday, I think it was, that us priests, we got an email from the Archbishop that things are looking toward opening up. They want to do it in concert. He wants to do it in concert with the other dioceses of the region, which is the state of Florida.
Great.
However, we have a particular situation, as you know, down here in South Florida, which is essentially the 3 counties of Palm Beach, Broward, and Dade, being a hotspot, mostly because of population density, but also because of all the international travel and even national travel back and forth. So anyway, that involves 2 dioceses, the Archdiocese of Miami that covers Broward and Dade County, and then Palm Beach is its own diocese too. So there has to be special coordination with these 2 dioceses. At any rate, we hope and pray that we can see everyone in person soon, and especially that our laity may soon have access to the sacraments. All right, moving forward then, we have this course on environmental bioethics, like I mentioned, for the next 7 weeks. And so there are 7 modules involved. And here we're looking at the interaction precisely between the human person and our environment, our natural environment, and also our artificial environment, the one that we create, that we generate ourselves. Considering that we have looked at the human life issues in the previous courses, starting first with the evolution of the human species, And then this last semester looking at beginning of life and end of life issues for the human. Now we're going to continue expanding and look at our surroundings, because we certainly don't live in a vacuum. We live on a planet that, as far as we can tell so far, is the only one that is inhabitable for us and has the proper conditions, both with regards to temperature and atmosphere, water, everything else that we need for life as we know it, speaking of organic life. Okay, so the first half of the course, if you will, is going to be looking at the Earth itself, the physical and chemical properties of Earth, of planet Earth, beginning today with the geosphere. In other words, looking at very, very briefly the formation of the Earth to the point of where we are today, where we have a fairly solid crust that is very thin, essentially including the continents and the bottom of the ocean floor. Then next week we'll look at the atmosphere. In other words, the two fluids that are on Earth are gases and liquids. At the natural level, what keeps us alive and the rest of nature is the atmosphere and the hydrosphere. So we'll look at those two layers of Earth, if you will, the next 2 weeks. Then we're going to get into cycles, because nature is a very dynamic system that is constantly moving and renewing itself. So there are natural cycles, and also within that context, we'll look at recycling by humans, which has an impact, of course, on nature for better or for worse. Finally, continuing along, then we're also going to look at energy sources, energy production and consumption, and alternative energy sources, and so forth, okay? Then we're going to look at the human population in a little more detail, and what is known as the growth curve, the sigmoid growth curve, which is a standard pattern for the growth of plants and animals and fungi, bacteria on Earth, and organically we're no different from them. It's just that we have a very particular situation in that the whole, I've mentioned this before, the whole human species throughout the whole Earth is considered a single population, okay? So that means essentially that the whole Earth is our home, is essentially inhabitable by us. In great part because of the development of technology that allows us to live even in harsh climate, in contrast with other species. And then finally, the last topic, the most controversial one on climate change and global warming and so forth, all these controversial issues, we'll try to discern between fact and fiction, and see what is the human proportion of that climate change. Because in one sense, if we look at long-term climate, in contrast to weather, for example, is measured in long terms, minimally thousands of years, more likely in tens of thousands, or hundreds of thousands, or even millions of years. And there are natural cycles there that occur, warming and cooling cycles, of which we have geologic evidence, but we have to see what aspect of those cycles is anthropogenic, in other words, caused by us, by the human species, okay? And along these lines, also the encyclical of Pope Francis, which will be our textbook for the course. The encyclical is called Laudato Si, on care for our common home, is the subtitle, Care for Our Common Home. And it was published by Pope Francis in 2015. I can't believe it's been 5 years already. I remember when it was published, and we even developed an international conference on climate, nature, and society at St. Thomas University within a year of the publication of that encyclical. Very important and historic, actually, for our church, because in the 2,000-year history that we have of existence, it is the first time that an entire encyclical is dedicated fully to the environment, and of course to those who are impacted by drastic changes in the environment. And so, it's about 200 pages long also, so it's essentially a book. And we'll look at the encyclical as we go along the way, but as I mentioned previously in an email, you can start reading it already, all right? It has 6 chapters. And you can download it for free from the internet, or you can also purchase it for, I think, about $10 or $12. For example, there are several sources, but one source that I'm aware of is from the Conference of Catholic Bishops. They have a website, the U.S. Conference of Catholic Bishops, and they have a bookstore within the site. Okay. Okay. Questions or comments? No? As always, you can just stop me along the way if you have any question or comments to make. So that's an overview of the entire course there. Now, for today's module, sorry, someone had a question? Okay. Moving forward, I hope you can see my PowerPoint, yes?
No, there's a PowerPoint.
Let me raise my volume here. Okay, this little laptop has a small speaker. Please tell me.
I can see it clear. It's just that you have to play with the different types of screens and in Zoom.
So you can see it, yes?
Yeah, I see the power. I've seen the PowerPoint since you put it on the screen.
Okay. So that's my main focus is the PowerPoint, and of course after the lecture I'll send you this PowerPoint together with the link. It'll take a little bit to download, of course, and to turn it into a YouTube. Okay, but I'll follow the same procedure as we were doing previously. All right. So today we're going to focus on the geosphere. All right. And the first half of the lecture, and then we'll take a little break and come back to look a little bit at some basic concepts of ecology and how plants and animals and all living species interact with one another in these complex webs that develop in a very dynamic fashion. So with regards to the formation of the Earth, we're going to look very briefly a little review of the origin of the universe and then the origin of Earth, and then geophysics itself, leading to the layers and clusters of the Earth, all the way up to the crust of the Earth, which is where the continents are, and these theories of plate tectonics and continental drift. And then there'll be the break there, and we're going to get a little bit into ecology by looking at biomes, food web and food pyramid, and then doing the progression from populations to communities to ecosystems to biomes to finally the biosphere, which is the sum total of all life on Earth. So, moving forward. First, a little bit about the universe as such. This is a review from what we had covered 2 semesters ago when we looked at the origin of the species. I did a little bit on the origin of the universe and the origin of the planet Earth. I want to reiterate that we can classify, or astrophysicists actually can classify all of the components of the universe into these 3 basic categories, okay? Now, I don't claim to be an astrophysicist by any stretch of the imagination, but this is pretty much what they're telling us with regards to the sum total of the components of our universe, at least as we are able to understand it so far. That what we can call visible or normal matter / energy is only about 5% of the universe itself, only about 5%. What do I mean by visible matter / energy? It's literally everything that is surrounding us that we can measure, that is empirical, okay? So for example, this very computer in front of me is made up of material. It has weight, dimension, etc. But it also has energy, mostly electric energy or electromagnetic, whatever is running the machine electrically, all right? So, and we know that there is a conversion and an equivalency between matter and energy, which essentially was given to us by Einstein in that formula, E equals mc squared. All right. Let me put here. I'm going to use the caret so as not to delay further. All right, where E is energy and m is mass or matter. C is the speed of light squared. So this is actually an acceleration, all right? When we square a speed, excuse me, we get an acceleration. Meaning that if we were to take any mass and accelerate it to the square of the speed of light, that mass would turn into energy, and vice versa. So we can pass this product here to the other side of the equation in the denominator. And if we divide energy by the square of the speed of light, which is the fastest velocity in the universe that we know, okay, then that energy would turn into mass, back and forth. It's a theoretical formula, and it's theoretical because C, the speed of light, being the fastest speed that has been recorded in the universe, then to square that is a hypothetical situation, okay? The astronomers have not detected anything that actually is accelerating that fast. So it's a theoretical formula, but it gives us at least a framework for converting mass into energy of the visible mass or the normal mass that we know of that surrounds us. But again, with theoretical calculations, astrophysicists and others who study this are telling us that that only makes up about 5% of the universe, the known universe, all right? The other 95% is divided into these two other groups that are called dark matter and dark energy. But the dark is a different type of dark, all right? Dark matter, excuse me for a moment. Dark matter is dark because it is so dense that it doesn't allow light to exit. And for example, black holes, which have been detected already in space, are so dense, the core of the black hole is so dense that not even light is able to get out because gravity is so intense that is holding the photon, right, as a particle is holding it back. And we know, or astronomers know, about the existence of black holes precisely because when they look at certain parts of the sky, there are things that are missing, if you will. All right, there's an emptiness there where there should be galaxies and so forth, even behind the black hole, and they cannot see through because the observation is impaired by these phenomena. So that is dark matter, and it's estimated to be about 27% of the universe. But what is most intriguing is what is known as dark energy. all right? And dark energy is called dark, not because it's equivalent to the dark matter in the sense that it's dense and doesn't radiate anything out. No, dark energy is called dark because, as I was hearing a tape on Einstein precisely one time, we really don't know anything about it. We're in the dark about it. Okay, we're totally in the dark, or the astrophysicists are in the dark about this energy. They just know that it exists somehow because of what is known as the background radiation. The background radiation that is approximately 14 billion years old, which is about between 14 and 15 billion years, give or take 1 billion, which is the age of our universe, all right? What is called background radiation. And I'll tell you what that comes from in a minute in the next slide. So anyway, these are the components, so these are the percentages of universe as far as the scientists, the experts can tell us about it. So basically, we're concerned with this 5% here, okay, which is what, again, what we can measure, excuse me, what we can measure with the instruments that we have today. All right, moving forward. Then a review of this scenario of the origin and development of the universe as to the point where we are today here. Okay, beginning with this moment of singularity, or the Big Bang, all right, where all the matter and the energy is condensed into a single point, if you will, not a dot, but a point, geometrically speaking, which is just one dimension, right? One dimension that kind of explodes, for lack of a better word, from nothing, everything. And that is theologically the moment of creation. The one who gave us this paradigm actually was, if you remember, Henri Lemaitre, all right, who was Belgian astrophysicist and also a priest. He was a Jesuit. And he's the one who gave us this paradigm of the Big Bang, or the moment of singularity, which allows for both a theological explanation of creation and also the origin of the universe as we know it, that then as the universe develops, it goes through several layers or stages. And it essentially goes through two main stages, if you will. The very early stage is called an inflation, which is within the first nanoseconds, all right? Within the first nanoseconds, much less than a second in chronological time, all right? So the time that we count 101, all this inflation takes place from nothing to something. It's something very significant, which is the first layer of radiation, which is that one there. And that's what is known as the background radiation. Then comes a second development, second stage of development, which is known as expansion. And that's why it's represented kind of like a cone, all right? An expansion. And this is measured in the opposite end of the scale of time, whereas the inflation is measured in nanoseconds and microseconds and 10 to the 20 and 10 to the minus 30 seconds, all right, and even 10 to the minus 40 seconds. That was the inflation. The expansion phase is measured in millions and billions of years, at the opposite end of the scale of time, all right, to the tune of about 14 billion years, more or less. Here it's put at 13.7 billion years, give or take 1 billion or 1.5 billions. All right, so within these layers, then we can look a little more detail. And this is more of a chronological scale here, describing in 7 stages what occurred along from the beginning of time and space simultaneously, that time-space continuum that we talked about earlier. All right, the superinflation, you see it's measured 10 to the minus 43 seconds. All right, so here's 1 second, the first second of the universe, the first second of history. Then it goes through a second stage within that, that very, very short, fast framework where the subatomic particles are beginning to form, the quarks essentially, which then a few nanoseconds later continue to coalesce to form the subatomic particles, the classical subatomic particles that we know of, electrons, protons and neutrons, and then eventually a few nanoseconds later, they actually start coalescing and colliding according to charges into atoms, all right? And that then the atoms are very significant because the atoms stabilize these subatomic particles. And those atoms, which the simplest of the atoms is hydrogen, just one proton and one electron. And then they continue to coalesce into more and more complex atoms, helium, etc., until we get all the atoms that we know of today in the periodic table. And the scale changes into minutes and very quickly develops into thousands, hundreds of thousands of years, millions, and then billions of years, and so on, until we get to where we are today with the galaxies and the solar systems and so forth. So it's been a gradually coalescing or coming together of matter. Essentially, this process after that original incredible explosion that occurred. Now, without going into more detail there, because I simply just don't know it, we can look at the solar system as a preamble to the formation of our own planet. And there have been these 4 to 5 stages, essentially these nebulae, which are gas, all right, super hot gas, that as the atoms coalesce more and more with each other, they begin to form a gravitational field. And that gravitational field, as you know, is one of the 4 fundamental forces that we know of, then pulls more matter into its core, making this process of accretion, what is called accretion, which is as more matter comes together, it generates a stronger and stronger gravitational field with a further pull, if you will, further out, bringing in more matter yet. At some point, that matter is coming in at such a speed, such a gigantic speed, that the core explodes, all right, and forms essentially a disk. I have no idea why it is a disk and not another sphere, but the fact is that it is a disk, and it's significant because then that disk becomes the precursor of the planetary systems. Because then in combination of forces of the centrifugal force, the blobs of matter seeking to escape as they are rotating at extraordinary speed around the core, that will be the centrifugal force, right? Very much as if we were to spin a ball on a string and then let it go, that ball with the string will tend to go out perpendicular to the diameter or to the radius of the circle that we were describing as we were spinning that ball around, all right? And that's the centrifugal force. That is counterbalanced with the gravitational force of the core that is called a centripetal force pulling in, very much like this one here in the original nebula, all right? And the balance of those two forces, what happens is generates an orbit, so that these blobs of matter get trapped within this disk and begin to define themselves more and more as these blobs of matter go through the description of their orbit. They're also picking up other fragments of matter that are out there, in addition to other matter that may be passing by, happen to be passing by at that point, and is being picked up. So you can see it's an extremely dynamic system, but definitely has some sense of order to it. And the order is provided precisely by the balance and counterbalance of the forces that are acting upon these disks, all right? Over periods of time, measured again in billions of years, these disks become planetary systems, which typically have a sun at the core, a star at the core, which is gas. But imagine the amount of gas there is so large and so dense that it is actually exerting a gravitational field, keeping the planets, meaning the other blobs of matter that got to condense further and cool somewhat enough to form solids, but also with liquid and gas on them, talking about the planets, and trapped into the gravitational field of that star to form planetary systems, okay? This is known as the planetesimal hypothesis. It's a hypothesis because how do you prove this, right? It takes several billions of years to prove it because that's how long these natural phenomena take to form. And that time has been measured to the point that it's estimated that our own planetary system took about 4.5 billion years. So out of the 13.5, so our planetary system, which is part of a galaxy called the Milky Way, actually began this process about 9 billion years into the expansion process, right? Okay, and again, just for reference, you can see it here, the formation of the galaxies. And actually, galaxies come together to form these super galaxy structures. And from here, eventually, the planetary systems develop. Okay, let me move on to where I really want to go, which is the planet Earth. So again, to put it in the framework of our own planetary system, what we call the solar system, our sun is a star, which is a gas giant, which is in flames. It's mostly hydrogen that is, and it's a ball of fire. By the way, I want to talk about the issue of the ball. Why do stars and planets look basically round, spherical? What is keeping them spherical, what gives them that shape is precisely in gravity. The gravity that is pulling in the mass, but because it is floating, if you will, in a three-dimensional space, then there are no constraints in principle on the shape from the environment, meaning the space around it, and it's three-dimensional, so the most uniform and the most efficient shape in a three-dimensional space is the sphere, all right, or some approximation of a sphere. We know that our Earth is actually a little flattened on the poles, so it's not an actual total perfect sphere, but it is spherical in shape. So are the rest of the planets and then the sun itself, all because of the pull of gravity at the core, which also means that typically the core is the most dense part, either of the star or of the planet. Going further from there, it turns out that we have in our solar system that have been discovered, okay, we have 4 inner planets and then 4 outer planets. All the names are there. We are the 3rd one out from the sun. And that is significant because we happen to be at the distance from the sun that allows for liquid water. All right, liquid water, which is the basis of organic life, at least as we know it here on Earth. And it's a very, very narrow margin of opportunity, if you will, of temperature, essentially from 0 to 100 degrees centigrade, which is very small compared to the temperatures, to the very cold temperature that is in the rest of the universe, and the very hot temperature that is right at the sun. So we are in a very, very narrow range of temperature that allows for liquid water. Okay. And another, just some interesting little details here. The outer planets actually are known as gas giants, meaning that they are mostly gas, but still it's very dense gas, and they have these huge storms going on the surface, but the layers of that gas, and typically they have some kind of a solid core that is maintaining the planet together. All right, but so basically what I'm trying to say by all this is that the planets are maintained together and spherical because of gravity, of the inner gravity of the planet itself. Then there are these dwarf planets that are called, which so far 5 have been identified. Okay, Eris, Pluto, Makemake, and Haumea. And I only see 4 here. There's, oh, Ceres over here in this inner belt of asteroids, yeah. Remember, you may be old enough to remember that Pluto used to be considered the 9th planet, but it has been demoted, if you will, to a dwarf planet. And the dwarf planet is not necessarily a reference to the size, as another characteristics, I didn't know this, but I looked it up the other day actually, is that these are known as dwarf planets more because they have not yet cleared the debris in their pathway, okay? And that's, the size actually is a consequence and not a source. The others are larger because, like the inner planets, for example, in their orbits, they have already cleared other debris that may have been in that orbit and picked it up and integrated it to the planet itself. And that's most likely why they got larger. Okay, so these guys, the expectation is that over a few more billions of years, as these dwarf planets continue to orbit around the sun, they will be clearing more and more of the debris that is there or gets in its pathway, and thus increase in size, all right? Okay, tidbits of curiosity. There's a lot of curiosity with regards to the solar system and the universe that we certainly don't have the time to get into, or the knowledge anyway. So not an expert at all, but just want to move forward to look at the formation of our planet, which is typical. We see other planets also at different stages of this formation, but it's this process called accretion. Again, it's kind of a 2-step process from accretion to differentiation, okay? And it's going to be what is known as an inhomogeneous accretion and differentiation. This is what I mean. First, beginning by the coalescing of this ball. Essentially, you can think of the largest, the most dense ball that was out there within our particular orbit. Okay, in other words, at this particular distance from the sun on the disk, as that disk was rotating at that fantastic speed. So the largest ball there of matter, started pulling in by gravity other debris that was around it, also spinning at some speed and so forth. And as that debris was being pulled in with an increasing acceleration, because we're talking about gravity, right? It's not just speed, but it's acceleration. It would smash into the ball, making it more dense, and at the same time adding its own mass to the original blob that was there. The end result is that this mass keeps getting larger and larger, but also with time, inexorably cooling because of dissipation of heat, which is part of this order, or entropy, meaning the passive radiation dissipation of heat. As heat dissipates from this mass, then it begins to cool, of course, or cooling further into forming eventually 3 layers of solid, liquid, and gas. But the layers also trapped within the mass itself, so that the end result is we come up with 5 layers. There are 2 core layers, then there are 2 mantle layers, and finally the 5th layer is going to be the crust on the top. All right. Again, for reference, the temperature range at the crust, not at the core. All right, the core is several thousand degrees hotter, but at the crust, at the outer surface, is this range from 0 to 100, which allows for liquid water. Okay, so accretion basically is just a fancy word for coalescing and accumulating, all right, coming together. And inhomogeneous because of the layers, because it has several different layers that are composed of different elements. So let's get into those layers briefly here. Again, here are 2 cores. There's an inner and an outer core. Then there's a lower and upper mantle. And finally, the crust, which is pretty much solid where the continents are. And that this crust then is going to get us into looking at plate tectonics and seafloor spreading and the theory of continental drift. What is moving these plates, which are essentially the continents, is something called convection currents, which I'll show you a little video in a minute. Okay, so back to a slice of the Earth here. Again, the inner core, which is solid, interesting, is solid, mostly iron, all right? Solid iron is at about 6,000 degrees centigrade. This is known as white hot, right? If ever you have an electric stove or you've seen one of those, and you turn on the stove at the highest setting, it turns red hot, right? It turns red hot, which is very hot. It radiates out and it's dangerous and so forth, and hot enough to cook food and boil water, etc. But if one were to continue to heat that coil, heat it up, and the coil was able to resist that heat, it would go beyond red, it will turn white, all right? And white hot actually will radiate photons out, light energy will be emitted in the manner of photons. In fact, again, if we can remember incandescent bulbs before the LEDs and before the neon lights, right? Some of us old enough to remember incandescent bulbs. When you had to change one of those, you had to wait until it cooled down, because if you touched it, it was very hot, right? Well, the little filament inside the incandescent bulb was actually getting white hot. White, as in the word white, okay? W-H-I-T-E. And it's white simply because it looks white to the eye. In other words, it's emitting photons, light energy, white light, which is the dirtiest. In other words, it has the full spectrum of the visible spectrum of light that the eye can detect. So that's the core of the Earth, all right? It's also so dense that it's keeping the rest of the Earth together as a sphere, as I mentioned. Then there is an outer core beyond it, which is about half the temperature, down to 3,800 degrees centigrade. And this one is liquid. This one is liquid, the outer core is liquid. Then beyond that, there is the mantle, which again has a lower and an upper mantle. And the mantle, again, is molten. The mantle is molten, which is liquid but thick, all right? And lava, for example, is mantle, okay? When the Earth cracks, when the crust cracks somehow, and spews out that mantle. That's what we call lava, all right, which is red hot, okay? So we go from white to red hot in a difference of about 3,000 degrees. And then imagine the crust is so effective in keeping heat back, that we can go for just through the crust, which is a few kilometers thick, right? About 100 kilometers here. We can go from 3,000 or 2,000 degrees to essentially 0 degrees centigrade, or minus below 0 to solid water, okay, to ice. So the crust is an incredibly effective heat shield. And that allows, in part, for having life on Earth, the crust. But very thin when you compare that it also goes about 6,000 6,000 kilometers from the core of the Earth to the surface. It's kind of interesting that it's both in the thousands, the temperature and the kilometers to the core. It's around 6,000. It's a coincidence, actually. But by the time we get to the core, I mean to the crust, which comparatively is very thin compared to the 6,000 kilometers, only 100 kilometers, we can go from 6,000 degrees centigrades to 0 degrees centigrades, okay? All right, so very interesting, unique properties of Earth, all this pointing to the fact of the possibility of actual organic life. Now, at this point, if you're thinking scientifically and analytically and critical, one could raise the question, well, how do we know all this? No one has ever been down there, and certainly a probe has not gone that far in, and it would melt anyway and so forth. So how do we know all this? And also the chemical composition of the core and the mantle, which the core being mostly iron, for example, which is the most abundant element on Earth, and the mantle being mostly magnesium and even oxygen and so forth. Well, we know it through earthquakes and measuring the wave, all right, the time of the wave and the intensity of the wave as it is reflected and refracted on other parts of the Earth. So let's say that there is an earthquake here at the North Pole somehow. All right, that earthquake is going to generate a wave that will radiate into the Earth, all right, and will it be either reflected by the mantle or the core. In this case, it's showing the outer core here, okay, will be reflected. Or if it penetrates different types of waves, different wavelengths, because the earthquake will generate actually a cluster, a range of waves, okay? Some of those waves are shorter, some of them are longer, they have more penetration quality, all right? So some waves will be reflected from the outer core, for example, and be detected at other parts of the Earth. Other waves will penetrate somewhat, but as they penetrate and go from one layer to the other, all right, it's just similar to light going through different density from glass to water, for example, or from water to oil, etc. That wavelength will diffract, in other words, will bend, will bend, and then when it comes out on the other side, will refract again and so forth, and will be picked up at a different time with a different intensity. So long the short, for seismologists and people who are in the know about this, they measure all these different waves that are detected at different parts of the Earth, right? Because they have seismographers there that detect this. And they're able to figure out, depending on the time and the intensity from the original event of the earthquake to where it was detected, where on Earth it was detected. Of course, the distance is already known because of the sphere, right? One can estimate the sphere using pi to estimate the diameter and the radius of the sphere. And then the time it takes and the intensity with which it arrives, they're able to estimate knowing again the qualities of these elements, of the various elements from lab experience, they're able to estimate what is the thickness and the density of these elements inside, okay? And the long, the short of all that is that the core is made up mostly of iron. Don't expect you to know any level of detail here, just simply that essentially the core is iron, and it causes that pull, gravitational pull, because it is iron. It is a fairly dense metal. And then the mantle is mostly silicon and magnesium and oxygen that is also trapped in there, all right? Whereas the crust has the rest of all the other elements that we know on Earth on the periodic table, okay? So most of the elements on Earth are literally on the surface of the Earth, the crust of the Earth, the elements that occur naturally. All right, let's move forward. And this is to have a little background to the convection currents, all right? With this mantle, let me show this as a primer, if you will. These convection currents that make the mantle move, literally move and circulate in its area between the core and the crust. There is this thick layer of mantle, which is about 3,000 kilometers thick, all right? And that layer, even though it's thick, but it's molten lava, so it is really a liquid. It's a thick liquid, and it's moving. And it's moving by this motion that is called convection currents. So here's a little video that illustrates convection currents. So a few minutes long. I need to copy and paste onto the website. Here we go. Oops. Paste single. All right. It has a little background music that is kind of dramatic. Try to ignore the music a little bit, but the phenomenon itself, it uses ink to show convection currents, the phenomenon of convection currents, which happens as a liquid is cooling. As a liquid is cooling, it will gradually move toward the surface, but if it is stopped at the surface, then it will move along the surface, and as it cools on the surface, it becomes more dense and then drops down again toward the bottom of the container, which in this case is the Earth. And at the bottom, then the bottom heats up again. As it heats up, it starts rising, as we'll get more later. Maybe I thought that is so many things. So. In the time space, I'm changing the PowerPoint. It's a PowerPoint is this phenomenal convection current. What that does is that the mantle, all right, is actually circulating in this fashion. And here is kind of a column, but actually, if we look at it in three-dimensionally, it becomes like a ridge, all right? And it's pushing mantle up. And when it gets to the crust, the bottom part of the crust of the Earth, which is here, it actually slides the crust to either side. It separates the crust and moves it sideways. And it will push to either side in opposite direction. And that is what is known as seafloor spreading, okay? Seafloor spreading, which I think I have here. Yeah, seafloor spreading, all right? So you can imagine that actually the Earth, even the crust of the Earth, is a dynamic system that is changing. I mean, we stand on the shore and we look out to the ocean and we can imagine the bottom of the ocean, right? The sea floor, and if we went down to a submarine, I would see it pretty static to us. It would look like unchangeable, but it's not unchangeable. It's actually dynamic. It's just that it's a very slow motion, because things that are in such a large scale move very slowly. But the end result is that, in fact, the plates, the crust is fragmented into plates or continents. The continents are either moving toward each other or moving away from each other. And for example, if this were Europe over here, and this were the United States or North America, Europe and North America are moving away from each other at a rate of about 1 inch per year, 1 inch per year, which is pretty fast. You know, in geologic time, we measure time in hundreds of thousands or millions of years. So that's 1 million inches in 1 million years, and that starts getting significant. And these plates are moving around. And that's the whole theory called tectonic plates, all right? So let's move a little further on this. Here I'm showing a world map with the main tectonic plates that have been identified. In fact, you can see that North America is one huge tectonic plate, including Greenland, and then Canada on the top, and even into Siberia, part of Russia today, and including the Bering Straits over here, what is today Alaska and so forth. That's the North American plate. Then there is the Eurasian plate, which is Europe and the rest of Siberia and Asia coming over here, including part of Southeast Asia here. Then there's the big Pacific plate, right? And the rim, that's the famous Ring of Fire. This Pacific rim here is called the Ring of Fire because it's all volcanic activity. Then there's the South American plate, the African plate, the Indian plate here, and then the Australian plate and so forth. And then there is one at the very bottom, which will be Antarctica plate. These plates are moving either toward each other or away from each other. The arrows are pointing toward that. But also, if we look at geologic time, in the millions of years, not even billion, all right? Keep in mind, so the Earth, we're talking about 4.5 billion years. Here is within the last 1/4 billion year. In other words, if we start at 250 million years, which is 1/4 of a billion, right? Fairly recently, in other words, in the history of the Earth as such, it was all the crust of the Earth was basically concentrated, the continents, in one huge plate, one mega plate known as Pangaea, which again is a Greek word for Gaia, or Gaia is a reference to Earth or the goddess of the Earth. And Pan is all or everything, all-encompassing. So the all-encompassing Earth was one huge megaplate, which cracked at several spots and started migrating out. It took about 100 million years, more or less, approximately, a little less than 100 million years, to separate into two main plates, a northern plate and a southern plate, more or less taking the equator as the dividing line, approximately. The northern plate known as Eurasia, and the southern plate known as Gondwana or Gondwana land. Also, you see that in the literature, okay? And continue to split, so we go around like this clockwise. Within another 50 million years of that main split, further cracking of these plates and moving away from each other, all this caused by the convection currents underneath in the mantle, all right? And separating, dissipating these plates from one another, general movement outward from each other. But by this time, we certainly have plenty of life on the continents, all right? Even back here, we have already living organisms, plants, animals, bacteria, fungi, etc. And so they get locked into these super islands, if you will. They become isolated, literally geographic isolation, which is one of the conditions, let's say, that can foster evolution, the geographical isolation of what used to be a single species, then by that isolation and variation, natural selection acting on variation, and you can see that it would be different climate and weather patterns and so forth in these areas that would start doing some selection process. And to the point that we have the continents today, the 7 or 8 continents, if you count India as an actual continent or subcontinent, whatever. The point is that all these were already populated by animals and plants and others and split. So, for example, in South America, the llama and the vicuña and the alpaca and all those animals that live in the Andes basically are camelids. They're associated with the camels and dromedaries of Africa and Asia, okay? And they used to be in Europe also. In fact, they used to be in North America also, different species, all from one original common species. And many other examples of plants and animals that way. That comes under the phylogenetics that we studied briefly in the first semester. Okay, so this is the continental drift of plates or plate tectonics, right? Because the tectonic is the actual the seismic activity that is generated by the movement of these plates, and that's why all of these boundaries are geologically, they're active regions of volcanic regions and mountain ridges and so forth. But some are on the water. In fact, some are on the water to the tune that the largest mountain ridges are in the bottom of the ocean, actually, that are huge, by far larger than the largest mountain range, mid-range, that we have on Earth, on the surface, which is the Himalaya mountains, okay? I'm thinking, for example, okay, so here on this slide, you can see the different plates named and the general motion in which they're moving either toward each other or away from each other. And that is going to cause either buckling up or seafloor spreading and so forth. I wanted to get to this map here, which is from the National Geographic, is a geographic map. It's a geophysical map, right? Where it's not showing necessarily the division, the political division of nations, but rather the natural contour on Earth, including the ocean floor. And you can see the two main features that we can see globally is this mid-Atlantic ridge here, and then the Pacific ridge, the Indo-Pacific ridge, because it begins in the Indian Ocean, actually. Here's India, the Himalayas. All right, the Indo-Pacific ridge going underneath Australia, between Australia and Antarctica, and then looping up toward North America. So these two ridges, the Indo-Pacific and the Mid-Atlantic ridge, are precisely, they coincide with that upper part of the convection current, where the mantle is literally spewing out underneath the crust and moving it sideways to either side, okay? Well, you can imagine that at the opposite end of the current, of the convection current, that mantle is moving downward. As it has cooled here by dissipation of heat, it will move down, all right? So eating into the plate, that would be here, this would be the Pacific plate, and rubbing and taking some of the crust, the lower crust with it, and liquefying it literally with the temperature, but at the same time generating crevices where some of the mantle will spew out, and that would form the volcanic region of the Pacific Ocean, the Pacific Rim. And so all of this, you see the ridges here, these are areas where the floor of the ocean is going down and buckling in and buckling against the plate of the Indo-Pacific plate here. And all this is volcanic activity. And the whole rim of the ocean, cannot see it on this scale, but down here would be all the Polynesian islands that spread along the South Pacific, all right, which is also volcanic islands. And then the volcanic activity on the west coast of well, South America, Mesoamerica, and into North America. All this is known as the Ring of Fire. The Ring of Fire because all this has volcanic activity that spills out periodically. And it's part of that mantle recycling, if you will, and cross recycling caused by convection currents. Okay, let's move forward now. At this point, we are going to look at the biome. So here's a good spot for making the little break. We're going to leave behind on the lecture the geophysical aspect of the Earth, and we're going to start looking at the life that is occurring on the surface of the Earth, literally on top of the crust, as I mentioned, that is cool enough to sustain life, organic life with liquid water. And we're going to look at both on land itself, on dry land, and on the ocean, okay? With the different groups and categories that are used in ecology. So just like a little ecology primer, so that we're familiar with terms that appear in the literature and sometimes appears in, as we dialogue, as we converse in bioethical issues of the environment, we have to be knowledgeable, we have to be competent in speaking about these terms: ecosystem, community, population, biome, biosphere, all right? And the food chain and the food web. So I'm gonna break here for a few minutes and come back into that living aspect. We're going to layer life, if you will, hypothetically on the surface of the Earth in the second half. Okay, so any questions or comments before we take a little break here? Nothing? Okay, in case you have difficulty communicating through the Zoom itself, I have my cell phone with me, so you can always call me or text me if you're trying to get a hold of me, all right?
Yes, okay.
All right, so let me pause this, and I see it's 11 o'clock. So let's start again at 11:10, is that okay? 11:10?
Yes.
All right, if you need more time, just do whatever you need to do, but I'll continue. I'll start the recording again at 11:10, and then you can pick up when you see the video, all right? So let me see, I want to pause recording here. Okay, here we go. Okay, students, welcome back. Restarting, okay? So we're going to move forward now to look at the life that is populating this wonderful and interesting planet of ours that we call Earth. So again, the big picture is that we have at the largest level, all of the life on Earth is known as the biosphere, and it is subdivided into large regions, about 9 large regions that are called biomes, all right? The biomes, again, the root here is bio meaning life. So these are large swaths or regions of Earth where life occurs. And again, we're talking about animals, plants, fungi, bacteria, the main categories of animals that we have seen, of living organisms that we have seen back in the first semester. And you can see that more or less they follow a horizontal stripe or zonation that is called horizontal zonation. The equator being here, which first thing I want to point out here or remind folks that you notice that most of the land mass of Earth occurs in the northern hemisphere, okay? In other words, here's the equator, and you can see that what we have south of the equator, we have about 3/4 of South America, okay? Pretty much coinciding with the Amazon jungle here, tropical rainforest. Then the lower part of Africa, again coinciding with the Congo rainforest. And essentially Australia, and of course Antarctica, which is not shown down here. But most of the land mass on Earth occurs in the northern hemisphere. In other words, everything else is up here, okay? And therefore, also most of the terrestrial life is going to be also in the northern hemisphere. And that's why you see pretty much all of these 9 regions or biomes represented in the northern hemisphere, and some represented in the south also. But if we begin at the equator, what the difference is going to be moving either north or south is the temperature. And when we get to next class, next Saturday, I'll explain a little bit how the temperature varies, okay, and the misconception that the poles are further away from the sun than the equator, even though theoretically that is true. The sphere of the Earth is so tiny compared to the huge ball of the sun that that difference of distance between the equator and the pole with regards to the sun doesn't really account for essentially 100 degrees of differential temperature here. Okay, it's a different phenomenon. Is the angle of incidence actually of the sun rays that make the difference in temperature. We'll get to that next lecture, next week, yeah. But now I want to point out that the warmest region on Earth is indeed along the equator, and that's where we have the tropical rainforest, the green represented here, okay? And then as we move north or south, but mostly north, precisely because we have more land mass, we go into region known as savanna, and then a desert, which is mostly in Europe, but also the Arabian Peninsula here, the center of Australia, which is one huge desert. In Asia, several spots, and then in North America, just off the Rocky Mountains, also the Trophic region, and even a high desert that is wedged in there in the Rockies. Going further north, there is this region that is mostly around the Mediterranean. It's called Chaparral, mostly along the Mediterranean, but also there's this little sliver of it in California, and the west coast on the Pacific, which essentially is a dry climate that is very rocky and right next to the ocean, all right? And it generates particular climate and weather conditions so that the flora and the fauna that live in this region is fairly unique, and it's called chaparral in general. Then we get into the temperate regions, the pinkish color here, the cream color band, if you will, mostly again in Asia, Eurasia, Eastern Europe and Asia, Central Asia, and the middle of North America going into Canada. This is the temperate region, which can be either temperate forest or temperate grassland, right? Deciduous forest, meaning that it is seasonal. It varies through the season. There is a spring, summer, fall, winter, and each season the plants are adapted and the animals are adapted seasonally that way into their life cycle. And then we get into the northern regions where we have the coniferous forest or the pine forest. in this light blue here, which is pretty vast and extensive, essentially mostly Siberia, or actually just south of that. Siberia will be a little further up. It's more tundra region here, grassland. But the coniferous forest in the northern part of Europe and Asia, and also mostly Canada, what is known as the Northern Territories in Canada, right? And then finally the tundra, where typically there is permafrost, meaning that the ground is frozen. Water is so cold up there that the water actually, the temperature goes below 0 degrees, and therefore the water freezes 1 or 2 feet or even less below the surface of the soil. So there's not enough soil or liquid water available for trees to grow and develop roots. Okay, so the vegetation here is restricted to small grasses and shrubs and so forth. And weeds, what we would call weeds, that's the tundra region. It's underneath the ground, it's frozen, and it's known as permafrost. Okay, so that's an overview of these different biomes, which are the largest categories of life on Earth, or regions. Now, what we need to do is we need to look at, and this is called horizontal zonation because it fans out from the equator either to the northern hemisphere, to the North Pole, or in the southern hemisphere to the South Pole, okay? All right, there's another phenomenon called vertical zonation, which is kind of equivalent, but it occurs by going up a mountain rather than moving either north or south geographically. But the net effect is about the same on the flora and the fauna, again, because the main factor driving this zonation is temperature. So as we can start, let's say in South America, in a region that is tropical. So here's the equator, but the Andes are here, and you can see this sliver of deciduous coniferous forest, right? The light blue, and even a little streak of white, which would be a polar or high mountain ice, including some icebergs up there, right through the equator region, which horizontally is very warm, but vertically it's a different story, because we know that as we go up a mountain, for example, the temperature drops, right? Temperature drops, and therefore the flora and the fauna also adjust to that decreasing temperature. So we can start at the base of the equator, say at the base of the Andes, say the Amazons, with a tropical rainforest, which has a lot of biodiversity, right? On land, the areas that have the largest biodiversity, different species living together in a particular region, are the tropical rainforests. And as we go up the mountain, it will turn to a deciduous forest. In other words, the climate and the weather will be seasonal, all right, experiencing the different seasons of the year, of the equivalent of that, even if geographically we are at the equator or near the equator, because the temperature is cooling. As we continue up that the mountain slope, it will get cooler, and so it will be the coniferous forest, okay, the pine trees, which are also evergreen. In other words, they keep their needles throughout the winter time because they are adapted to colder weather. And essentially, instead of sap, they have resin, and the resin doesn't freeze, and the tree does not become dormant, but continues to function, continues to photosynthesize throughout the winter time. Eventually, we go further up the mountain and we get into the tundra region, right, where there would be permafrost under the surface of the earth. So roots are not able to penetrate into that ice, and therefore this tundra region is limited to shrubs and grasses and herbs, but not trees, okay? And then finally, we move further up, and even the tundra disappears and we get into the icy region, where one could have the equivalent plant animal life as we would have in the poles. Okay, but the thing that is definitely missing up here, of course, is the ocean, because most of the life in the two poles is a marine life, right? And a life that is either marine 100% into the water or is dependent 100% on the marine life, like the penguins and even the polar bears and so forth, that feed on animals that either live in the ocean or themselves feed from the ocean, like seals, sea lions, etc. Okay, so that's what would be missing up here on the mountaintop, but the condition is very similar in the sense that it is all ice. Okay, so that's the other phenomenon, the equivalent phenomenon that is called vertical zonation, as opposed to horizontal zonation, but we get a very similar effect of the vegetation and therefore of the animal, the fauna that lives within that vegetation. Okay, here we have then a comparison of the geophysical world. Again, these are maps of the National Geographic. I showed you this map in a larger scale earlier, where it shows the surface of the Earth, the crust, both on land and the ocean floor. And then this one is the geopolitical world. In other words, what we've done with it, the almost 200 countries that we have, or nations of the world, 190 something nations, all right, with all their boundaries and so forth. By the way, I'm told that with 4 colors, only 4 colors are necessary, 4 different colors are necessary in order to illustrate all of the countries of the world without overlapping a color for 2 countries. And you can see with only 4 colors, or 4 different colors, all of the countries of the world can be represented adjacent to each other without overlapping on the same color for 2 different countries. Just another trivia thing. All right, so, and this in anticipation, because who makes these geopolitical world? Well, us, the one species of the 2 million that have been classified so far, approximately, this one species has taken the prerogative and kind of the arrogance, if you will, of dividing the geophysical world into a geopolitical world and staking out our property, as it were, by nations, and then within nations by, well, states, counties, and down to the block where we each live, right, throughout the world. All right, so this is the challenge here, that human beings have done this to this, and that is not without its effect. And that's what we have to look at in the complexity of the bioethical side of things. But what I say is we have to live somewhere, right? We can't live on thin air, just floating around. We have to live somewhere geographically, but wherever we land, our footprint is going to have an impact, and how to minimize that impact so it doesn't end up destroying the Earth. Even from a selfish reason, because that would end up destroying our own species too. So a lot of things to consider. Okay, moving forward. Now some little primer on ecology here. Ecology, one simple definition is the complex web of relationships between organisms in nature. All right, so it is a complexity, is the highest complexity, if you will, and you'll see it precisely as we follow these different layers of the complexity. Again, the simple analogy of the onion having so many layers, right? Just like bioethics, we look at the nature first. So is the relationship with these, between these organisms and among these organisms that forms this whole field or science of ecology, right? Studying the ecosystem, the logos of the ecosystem. All right, so some key concepts here with regards to food or trophic levels. We're going to start by looking at a simple food chain, which doesn't really exist in nature. Well, it exists at the most local level, but really this chain, this food chain, rapidly becomes a web, right, in nature. And then simply if we quantify the web by biomass, in other words, by organic material that is being produced and consumed by the next trophic level, we end up with a food pyramid, all right? So these three key concepts here, the food chain, the food web, and the food pyramid. And then we're going to go from population to community, from community to ecosystem, from ecosystem to biome, and finally the biosphere as a whole Earth. Okay, so let's look at these trophic relationship or trophic levels. Trophic is a reference to food, right? Again, because scientists, they don't want people to understand what they're talking about, so they use these fancy words, but this is another way of saying trophic is just food or feeding. Starting with a simple chain, right? A food chain with three organisms. We start always with a producer, which is going to be a vegetable, it's going to be a plant, it's going to be an organism that photosynthesizes. And so that's the reference to producer is producer of glucose specifically, okay, through the process of photosynthesis. So that is the bottom line core reaction, chemical reaction, organic reaction that allows for life on Earth is photosynthesis, which is taking inorganic compounds like water and carbon dioxide and mixing them and reshaping into a new molecule, which is going to be an organic molecule called glucose, or a type of sugar, a carbohydrate. And there's going to be a byproduct of that reaction, which is oxygen. So how about that? This process of photosynthesis takes water from Earth and takes carbon dioxide, which for us is a pollutant, if you will, and combining these molecules through this organic process of photosynthesis, the end result is the glucose molecule, a carbohydrate that has high energy, and a byproduct of the reaction is oxygen, which is actually the oxygen that we need and breathe for life to occur for the consumers. So in this process, the ones who benefit really are the consumers, all right? But they themselves also contribute something to the producer, which is also vital, essentially the CO2, the carbon dioxide, which is going to be a waste product of metabolism, all right? Or another way of saying metabolism, by way of the energy equation, is respiration, cellular respiration. Okay, so here it shows two levels of consumers. The first level is a herbivore. In other words, it eats herbs, it eats plants. So herbivores eat plants, and these are also known as primary consumers because they feed directly on the producer. But then there's going to be a carnivore. Sooner or later, there's going to be another animal that eats that herbivore, okay? And that's going to be a carnivore because this fellow feeds on the flesh of the herbivore, all right? And therefore, it is a secondary consumer. The primary consumer is the one that feeds on the plant, and the secondary consumer is the one that feeds on the herbivore. All right, so this is a simple food chain here with three links, if you will. One producer and two consumers. You could also stop here at the herbivore level if there are no carnivores. And you would say, well, what on earth does that occur? It occurred for the longest time in Australia, actually. And that's why the herbivores in Australia got to be so large and big, like kangaroos and wallabies and so forth, because there were no carnivores originally. Okay, there were no carnivores, and therefore the herbivores were able to become very large because they were the top feeders, if you will, and so they were simply, that chain just had two levels essentially, had a producer and a consumer, many different species that developed as consumers, but just two levels of the chain or two links on that chain. All right. However, this simple chain doesn't occur like this very much in isolation, because you can understand that not only the owl feeds on the mouse, but maybe an eagle also feeds on the mouse. And the owl doesn't only feed on mice, it may also feed on possums or some other animals, okay? And even the mouse doesn't just feed on wheat, it can also feed on barley or lettuce and so forth, or carrots, I don't know. The point is that several different species are producers, many different species are producers, and herbivores also eat different species of plants, and carnivores eat different species of herbivores. And then there are also intermediates here, which are called omnivores. We'll get to that one. Omnivores, well, let's get to it. Omnivores are in the middle, and they can eat either animals or plants. All right, omnivores. They are in the middle. And then the top carnivores typically are larger. They're predatory animals. They can either be mammals or reptiles or insects or birds. But these would be what is known as the top carnivores. So this one is only showing 3 levels of consumers and then 1 level of producers. But it also introduces another level, which is not shown here in the simple chain because this is simplistic, right? In the web, it shows the saprophytes. Saprophytes are here on the side, and very important to understand these saprophytes, which are otherwise known as decomposers. Phyte, phytos, is loving, and sapro is death or corruption or decay. Okay, so these individuals, these organisms love dead stuff, saprophytes. And these are the fungi and the bacteria mostly. And thank God for the fungi and the bacteria, because otherwise we would be buried, literally buried, in miles and miles of decomposing, rotting animals and plants, and it just wouldn't be sustainable. Actually, we wouldn't be alive if it wasn't for these saprophytes. The decomposers that break down all of the dead organic material, all of the dead animals and plants, and even fungi that die and bacteria that die, they get eaten up by live fungi and live bacteria, okay? And it gets recycled. And these guys break it down eventually to phosphates and nitrates and other nutrients, which are then absorbed and reabsorbed by plants to continue the cycle of life on Earth, the trophic cycle, all right, of food or nutrients circulating through the web. Okay, so you can see all kinds of complex interactions here. It's a very dynamic state, and it's part of adaptation, right? Now, we can also quantify this because these are living organisms that have their own weight and mass and so forth, and lifestyles, if you will. So this can be quantified, and that's where we go from the web to the pyramid, right? So the pyramid is basically a quantified web, and the basic ratio here is this 10-to-1 ratio. So the mass, the bulk of the organism, whether it's a plant or an animal, when we quantify it, we call it the biomass, okay? We all have biomass, essentially are what we call weight, which the real, when we look at the scale, when we measure our mass, when we weigh ourselves, we're actually massing ourselves. We would have to add the pull of gravity, multiply our mass times the pull of gravity to get our actual weight. And the units of the weight is actually newtons, right? In honor of the one who discovered gravity and was able to give us a formula and quantify and so forth. So what we have is biomass. And the general ratio, the overall ratio that comes up for each trophic level is about 10-to-1. What do I mean by 10-to-1? This is what I mean. Let's take a top carnivore like the polar bear, right? Who feeds on seals, for example. And this polar bear, in order for the polar bear to put on 1 pound of weight, 1 pound of mass, the polar bear has to eat 10 pounds of seal, all right, 10 pounds of seal. So there's, if you will, there's a 90% waste in the process. Little waste that comes out the rear end of the animal. So for the seal to put on 1 pound of weight, it would have to eat 10 pounds of fish and so forth down the levels, all right? And so here I've just put the expanding units going into tens, hundreds, thousands, and 10,000s. So if we have a trophic level that has 1, 2, 3, 4, 5 layers, which is not uncommon, okay? We begin down here with the, actually here with plankton, which will grow in the ocean, and the plankton will feed a number of fish and krill and so forth. Actually, this layer should be here. And then the fish will feed on the krill, and the seal will feed on the fish. We can imagine both on land and on the ocean, we could easily imagine 5 trophic levels, right? It would mean that it would take 10,000 pounds of the first layer of the plankton, for example, the phytoplankton, to feed 1 pound of the top carnivore in whatever system, okay, with 5 layers. If it only has 4 layers, then it would be 1,000 to 1. But each trophic level basically is a 10-to-1 ratio. It's a 10-to-1 ratio. The same would occur in a temperate region where you have, for example, the grassland, the quail feeding on the grains of grass. And well, here this, they should have they should have another layer here, something that's feeding on the quail, and then the fox or the coyote, whatever, is feeding on the rabbit. But if you have 4 levels here, then it would be 10 to 1, 10 to 1, 10 to 1. It would be from 1,000 to 100 to 10 to 1 pound. For every pound of fox, that fox would have to eat 10 pounds of rabbit. And for each pound of rabbit, that rabbit would have to eat 10 pounds of grass, let's say, okay? The same in the tropical region. Wherever we go, we find these trophic levels. All right, and that can be turned into a food pyramid. Okay, let's move along, because when we put the human up here, then we do consume
Class is on.
a lot of biomass. Just for every single pound of mass that we put on, imagine with our processed food, there has been an enormous amount of biomass that has been used originally way down at the agricultural level to produce that 1 pound that makes my body, okay? All right. I'm gonna leave agriculture itself for a later lecture. I'm still looking at the hierarchy now of life, going beyond the individual organism. These 5 terms here, they are key terms and they have a specific meaning each. So let's go through them so that we understand. The first one is population, the level of population, and then populations form communities, communities with the physical environment forms ecosystems, and then several ecosystems coming together in a large geographic region form the biomes, the 9 biomes that I spoke of at the beginning, and then those biomes all together on the surface of the earth form what is known as the biosphere. So let's look at population first. Again, these words have very specific meaning in science, and it's important for us as bioethicists to understand the meaning of these words so that we may use them competently, all right, when we engage in bioethical discourse with others, so that our discourse may have credibility And people, others, may not say they don't know what they're talking about. All right, so first, population. And population are several individuals of the same species, okay? And that's why I've been saying all along that we humans are one population throughout the whole Earth. Very interesting. We're the only one that has that universal, that ubiquitous population throughout the whole Earth, all right? The only species. And here I'm giving you some examples. For example, in this pride of tigers, I think it's called a pride, yeah? How many individuals in this population? Well, 4. There's a mother and the 3 cubs, right? So there are 4 individuals in this population of tigers, all right? In contrast, in this penguin population here, there's probably maybe 100, 200. I haven't bothered to count them, but there are quite a few. But these are all, I guess they're emperor penguins or the same species. This guy is also the same species, just turning around. But this is a population of penguins. Now, you see the little dots back here, all right? Assuming that these are also penguins, those may be and of the same emperor penguin species, the same species, but this would be a different population of penguins than this one. They're the same species, but they're not the same cluster. This is one cluster here, probably some kind of a clan that has a bonding between them, all right? They stick together, whereas these other groups here, these other populations of emperor penguin, the same species, have their own population, and they may not mix, or they may mix. There may be some interaction or not. All right, and how do these guys distinguish themselves from each other? Probably mostly by odor, but also by sight. Just like we would distinguish each other, but by what we humans call races or ethnicities, even though those are cultural constructs, they really don't have a biological basis to it, because it's, we can interbreed. The different races and the different ethnicities can interbreed, can indeed form, generate fertile offspring, right? And therefore, the construct of race or ethnicity is an artificial construct. It's a cultural construct. It doesn't really have a biological basis for it. If it did, we wouldn't be able to interbreed, okay? And that's also why the human population, all of the people on Earth are a single population. All right, so here's an example in animals of populations. The group that sticks together in a particular local area, in a habitat. It can be a small number or it can be a large number. It also happens in plants, of course. So a forest, a particular forest, right, is a population. You look at, you know, the forest, the slash pine forest there on campus is very dear to me. And those are, we have about 200 of the slash pine there. That's a population of slash pine. It's of the species Pinus elioti. There are other Pinus elioti in the county and in South Florida, the same species, but they form different populations, all right? One that is pretty drastically different in shape, in phenotype, if you will, is down south of the county, is what is known as the rockland pine, is still Pinus elioti, all right? But it's very thin and spindly, and it's a different population, even though it's the same species, all right? It also occurs in bacteria and fungi, so all living organisms clustered together to form these populations. So here's just a micrograph. This is a photo micrograph of cocci, in other words, round circular bacteria that has been colorized. And so here we see a colony, a bacterial colony is also a population, same species, more than one individual of the same species clustered together. So that's population, okay? Next level is a community. So a community is 2 or more populations within the same region, the same local region. So I can ask the question in this photograph of some kind of a reef that looks very poor. This looks like a bleached out reef here. but ignore the reef for now. This is just a local region. I can ask you how many populations make up this community of animals, all right? All right, so we would count. The most obvious one are the 3 turtles. So here we have 3 turtles, assuming they're the same species, hawk's beak or whatever turtle it is. They are the same species of turtle, right? So this is a population of 3 turtles. That's one. Then there are these banded fish, which could be sergeant majors, or I'm not sure, but these banded fish, 1, 2, 3, 4, 5, maybe this one that is facing head on. So the 5 individuals of a species of fish. So that's a second population. Then there are these other, probably a blue tang or something like that. And we have 1, 2, 3, and then there's another one here, which let's assume that it's also the same species. 4 individuals of the darkfish, right? Which is another population. So we have here 3 populations. This community is made up of 3 populations, okay, that we can see. Now, of course, if we were to go in here with a microscope and we start looking microscopically at all of these surfaces, we'd find huge amount of populations there of mostly algae and bacteria and microorganisms, coelenterates and other microorganisms that would be living, literally clustering all this, okay? But at least macroscopically, that we can see with the naked eye, is a community that is made up of 3 populations. And of course, each population is made up of a particular species, okay? Individuals of a particular species. All right, so on land also, here is another, now we've gone to an ecosystem. It's the next level up, an ecosystem. So an ecosystem, so we're trying to look closer and closer at reality, how nature presents itself to us in real life, all right? And when we look at nature in real life, we don't see just clusters of animals and plants and so forth. For example, here, all of these individuals are literally swimming and immersed within a liquid environment. That water itself, just the water, the salt water with all the chemicals that it has, is a non-living system. All right, so non-living systems are called abiotic factors or non-biotic. Remember, the A negates, it's the prefix that negates the noun that follows it. So biotic is a reference to life. Abiotic simply means non-biotic. The factors that are non-biotic are going to be essentially the weather and the climatological factors, okay? The temperature, the humidity, the pressure, what else is there? The amount of light, etc. Even the seasonal variations, okay? Those are all the abiotic or non-biotic factors that obviously affect the animals and plants that live there, right? And so when we combine the biotic factors, in other words, the communities, with the abiotic factors, in other words, the weather and the climate and so forth, then we get what is known as an ecosystem, an ecosystem. But we're still within a fairly small or limited region, a local geographical region. All right, so here, for example, we can see many individuals of different species, deer, raccoon, looks like a trout, turtle, crab, etc. Right? All of these animals, because they're different species, all right, together they form a what? A community. Also including the plants. The plants also, different species of plants. Some are trees, some are shrubs, some are grasses, above the ground and underwater. All of those are individuals forming their own populations, and together those different populations interacting form the communities. But then when we add, if you will, or we consider the abiotic factors, mainly the weather and climate factors, then we have an ecosystem. So you see, it's more complex. And when you include a time lapse, in other words, moving through the seasons, for example, then the abiotic factors also change dynamically, going from winter into spring to summer to fall, back to winter again. Those fluctuations have an impact on the lifestyle of all these different animals and plants, right? So that's the ecosystem that still belongs to a fairly localized region, all of the biotic and abiotic factors that live in this region. The only interesting thing that I wanted to point out here is, I don't know if you noticed it, but you notice that technically, from the definition of population, because populations imply two or more individuals of the same species, technically on this particular diagram, we don't really have populations because we're only seeing one representative of all these different species on the animal side. I only see one black bear, I only see one wolf here, or coyote, whatever it is. Well, maybe here, maybe the bears make a population if they're of the same species, right? But there's one fish, one turtle, oh, there are two more fish down here. Okay, so maybe that makes a population, but technically, we need two or more individuals of the same species to have the population, right? But you can use your imagination. Somewhere hidden in here will be another squirrel, another group of squirrels, and the deer, the rest of the herd of deers is around there somewhere, etc. Okay, so that's ecosystem. Then going further out or larger, when we look at large regions of Earth, which has several ecosystems, all right, covering several ecosystems, we end up with the biomes. The biomes, just roughly defined, is a relatively large geographical area that contains within it several ecosystems, all right? Sometimes a few ecosystems, sometimes many ecosystems, depending on how fertile or dry or harsh that biome, that region, that geographical region is. So the main terrestrial biomes are the tundra, like I spoke about, where there's permafrost, so you don't have any large plants growing there, and that limits the animal population that can also live on it. Then you have the forest, which can be either tropical rainforest or coniferous forest or deciduous forest, depending where they are geographically on Earth. Then you get grasslands and deserts, again, of different types. Okay, but these are the major, 3 or 4 major terrestrial biomes. It turns out that we also have biomes that are either freshwater or brackish water, brackish meaning the interface in between fresh and salt water, like estuaries, for example, all right, where rivers empty out into the ocean. And with the tidal pools coming in and out, the flow, the ebb and the flow of the tides, then this water will change salinity periodically, as much as twice daily, right, when the tide comes in and out. And so then it'll also change. The river is also a dynamic system. Depending on the season of the year, there's more or less water flowing through that river, pushing out. And so the estuary is a particular very dynamic system that is constantly changing in salinity. And therefore, the plants and animals that adapt to that region also have to live accordingly, right? By these tidal changes, by these seasonal changes that can be as drastic as several times a day, or even just once or twice a year, depending on the ebb and flow of the river itself. All right, so lakes and rivers also, and then marshes or swamps, which tend to be more fetid water, in other words, water that doesn't oxygenate much, right? Generates particular environmental conditions for the plants and animals that live in that region. So these are the major freshwater and brackish biomes on Earth. lakes, rivers, estuaries, and swamps or marshes. Then, of course, the oceans, which is the largest by surface, the largest part of the Earth on the surface, on the crust, as it were, literally sitting on top of the crust. You have these three main regions: the littoral region or coastland, littoral or coastland, all right? Or you have the pelagic region, which is the water column itself. And some animals, many fish and other animals, live all their life essentially on that column, water column, which is called the pelagic region, except for example, when they spawn their eggs, they need to go to the littoral region, drop their eggs, and then rush back out into the pelagic region, okay? And the vast majority of fish do that anyway. Even pelagic fish like sharks and large fish spawn their eggs on the littoral region and then head back out to open water. By the way, on this photograph here, how many populations do we have in this community? Visibly, we can say one or two. This seems to be a white tip shark, maybe. Anyway, it's a shark of some sort. And then it has underneath these fish, I think they're called pilot fish, right? And there's a cluster of fish here that are following. They seem to be all the same species. If we get closer to the shark, perhaps we could see some remoras that are clinging on to the shark itself, but we cannot see them on this thing. Anyway, this would be one population, the pilot fish. And then we can assume that this shark is, well, some sharks are loners, but they need to cluster at least during the mating season. There would be some other sharks of the same species in the region, or there could be sharks of several different species also in the same region. Those would be, each one of those species would be a population of its own, all right? And then finally, the benthic region. The benthic region is essentially the floor, the ocean floor. And the ocean floor could start at the littoral region and then start bearing down through the continental shelf and then down into the abyss to the deep ocean floor, 1 or 2 miles below the surface. And that's all the benthic region. Okay, and that also is stratified vertically. Mostly the main factor is light, or the amount of light that gets filtered out until eventually it's just blue light that penetrates. Most of the red and infrared gets filtered out in the shallow part within the first 10 feet or so of water. Okay, so you have most of the biodiversity and most of the abundance of life in the ocean is going to be in the upper 10 feet of the benthic region, right off the shore, typically, where you find the greatest biodiversity. And if it's in the warmer regions of the Earth, that's typically the coral reefs, right? Don't miss out on this photograph. One particular individual of the human population here doing some nice diving. Okay, all right. So those 3 regions for the oceans. And then that just leads us finally to looking at the biosphere as a whole. I want to point out that this is an actual photograph, okay, by the benefit of the satellites that are out there orbiting our Earth. We now have actual photographs of the Earth and how it looks in its very striking particular pattern that we haven't really found, or astronomers haven't found this particular pattern anywhere else yet of the planets that have been discovered or speculated, with the blue and the green in particular that are an indication, the blue being the liquid water and the green being the plants that photosynthesize by using that liquid water and so forth. So these colors could be an indication of life, extraterrestrial life somewhere else if they're found, but as far as I know anyway, I'm no way an expert on this, but these particular color patterns have not been found in any other planets yet. So you see the different components here. the geosphere, also known as the lithosphere, all right, lithos reference to rock. And that's mostly what I was talking about today, the formation of the Earth itself. Then, as I mentioned, next week, we're going to look at the atmosphere, which is one of the two fluids, natural fluids on Earth in large amount that is maintaining life. Essentially the air, which is a compound of many different chemicals. And that air is a fluid. It's a very thin fluid, but a fluid. So it obeys the dynamics of fluids, fluid dynamics, okay? And so the hydrosphere also, like I mentioned, the oceans, the rivers, marshes, lakes are part of the hydrosphere, including also the glaciers, which is solid water, right? And the ice caps, of course. Okay, and then the ecosphere would be the one that has life. All these together form the biosphere of Earth, and that is the concern for preserving this life on Earth, which is so unique, so special, and the fact that we are living on this planet that is racing through, speeding through the planetary system and through the universe at such prodigious speed. And yet here we look around the horizon and we see everything so still and quiet, these beautiful days that we have. Everything seems in such harmony, and yet we can cause havoc, literally havoc on the Earth due to our misbehavior, okay? And that is the bioethical dimension that we need to get into as soon as we understand a little bit more of the natural system where we are privileged to live. Okay, I'm going to stop here. Any questions or comments? You can let us know now or hold your peace. You can send it later if you wish, by email, whatever, or in your summaries. But again, let me stop talking for a moment and see if there are any questions or comments from anyone.
No.
Thank you, Father. Has been very thorough.
Yeah, no questions. Thank
All
you.
right, so just
It says that you're.
sorry, was there a question there? For some reason I didn't hear it. Let me check my, yeah, my mic is on and my speaker is on also. If someone had a question and got muted, I didn't hear it. If you want to send a chat, maybe we can look at it. Where's chat? See if there's anything here. No, empty. Okay. Okay, so basically just recapping very briefly the origin of the universe. I don't expect any luxury of detail on this, okay? I'm the first one who is an ignorant on it to begin with, but just a general sense of the main events on the origin of the universe, beginning with the from nothing to something, and then the expansion, the inflation and expansion, etc. Then the accretion process of the Earth to the differentiation, the inhomogeneous differentiation, right? The geophysics of the layers of the Earth, the core, the mantle, the crust, so forth, plate tectonics and continental drift. This is important because it has biological, geological, and biological implications, how the continents got to where we are today. And then finally, the biomes, the food web and pyramid, and how do we go from population, community, ecosystem, biomes to the biosphere as a whole. All right. Okay. Thanks again. And I'll be doing all the downloading and emailing as I do. So expect this later on today.
Thank you, Father.
Father, when is Father?
Yes.
When is the first of the next class, the math class? When's the first session of that?
The short answer is I don't know. Dr. Minea emailed me asking me when should she have it, and I said, look, it's your prerogative, it's your course. So I told her, just email the students and whoever, and just go by the majority when the majority are available. Being online, essentially, in principle, it could be any time, right?
Right.
So I just suggested to her to email you folks and then go by the majority of the people, and the rest will just have to watch the video and catch up and so forth. And it may even change from week to week, whoever is available at a particular time. But from your question, I can tell that she has not done that yet. So my suggestion is email her, okay? Email her. You should have access to the course already because you're all registered for it. So it's just that MAT 507 or 502. Be proactive, all right? You're at the master's level, so just email her and ask her when is it going to be.
What is her name?
Her name is Alia Minea. Minea, let me write it out here so you can see it. Actually, let's see. You can, you know, our emails are, they have the, I'm just getting to an email here because I don't want to misspell it. This is a little slow. Let me try it for a moment on my other computer, which may be a little faster. Explained. Oh, there we go.
Oh, there it is.
Oh yeah, okay. It's with an H, yes. I'm going to enlarge the screen here. Let's see if this works. There. Okay. Yeah, Minea with an H. Okay, so it'll be recorded on the video anyway, and you have, whoops, too big. Let me turn it down a little bit. Okay, it's this one here. Okay, there it is. M-I-H-N-E-A. Okay?
Okay.
All right.
Thank
Thanks
you.
again. God bless. Be safe.
Thank you.
Thank you, Father.
Bye, you too.
See you next Saturday, if not sooner.
you.
Thank you, Father.
Next Saturday. See you guys.
Thank you.
Bye.
Bye.
Bye. Bye.
Stop recording.